Hello everyone. So we are going to complete this unit. As you already have the PowerPoint presentation, this time I'm going to add an audio to the presentation so that the understanding becomes better. Okay, so we're going to start with the phase transition. So just basic definition, we know that matter transit make the transition from like solid to liquid or liquid to gas. So it's like just melting, boiling, sublimation. So that I think this is already known to you. So we are going to study this basically, okay, in this unit. So of course you might have studied this in your elementary classes, but what we are going to understand here is the role of statistical mechanics in this phase transition. Okay. So statistical mechanics basically involves the large number of particles, okay, and their arrangements, their different states, microstates, macrostates. So in phase transitions, basically the states, basically, uh, when the phase changes, the arrangement of atoms or molecules of that material basically changes. Okay, so such transitions involve the change in mutual arrangement of these atoms and molecules, and therefore of course, therefore the properties of the system will change. Typically, we are going to look at the thermodynamic properties in this unit. So we'll talk about thermodynamic potentials such as free energy, and we will specifically talk about Gibbs free energy here. One can also talk about Helmholtz free energy, which is this is what we have defined already in our previous classes, that free energy is equal to minus this 1 by beta times ln of z, where z is your partition function and T is the temperature and Kb is the Boltzmann constant. So this relation we have already derived in our previous classes. So in thermodynamic limit, we have to understand this particular thing, that what is thermodynamic limit. So thermodynamic limit basically stands for like when you have the number of constituents of the system like particles, molecules, or atoms very, very large, that you can say like infinite. Then we can have thermodynamic limit. In that limit, we can have equilibrium. We can explain thermodynamics by using statistical mechanics. So we'll have some discontinuities, and those discontinuities can only be explained only when we consider the thermodynamic limit. So the reason we are considering thermodynamic limit is otherwise the partition function, which is summation of exponentials, is going to be a continuous function. It's an exponential function. You can differentiate it infinite times and without any problem. So it is going to be a continuous function unless we have z equal to those summation over from for large number of particles like n equal to infinity. Then we can express this z, which can vary discontinuously. Okay, so just little bit of mathematics can tell you how uh, that becomes a discontinuous function when you consider n tends to infinity. So we'll mainly talk about two types of phase transitions here: first order phase transition and second order phase transition. Again, what we will see that the Gibbs free energy, we can express that in terms of its derivatives and all, and then there we will introduce the first order term and second order term. So basically in first order transition, the internal energy of the system and the specific volume of the system are the two main quantities, and based on that other quantities can also be discussed. So these are two main quantities, internal energy and specific volume, which are changed discontinuously during the phase transition. So for example, in solid phase it will have some value of internal energy, and in liquid phase it will have some different value of internal energy, and the change from this phase 1's internal energy to phase 2's internal energy will be very drastic. Similar thing for specific volume. Specific volume is, you can think like it's a reciprocal of density, right? Or sometimes it's just 1 by V. Okay, sorry, V per unit mass. Also, during the first order phase transitions, we will have evolution or absorption of heat. Okay, So basically there will be exchange of heat during the first order transition. So you might have to supply or extract the heat from the substance to so that it undergoes the phase transition. Whereas second order phase transition does not involve any discontinuities in internal energy and specific volume, and also does not have any exchange of heat. So the example for this is ferromagnetic to paramagnetic transition of, let's say, iron at QE temperature. Okay, so there it is a phase transition from ferromagnetic to paramagnetic, but it does not involve uh, the exchange or the absorption of heat, and also mm, it does not involve the discontinuities in the internal energy or specific volume of the system. Okay, so we will quickly see what we are talking about, the phase transition. So we have to understand the phase equilibrium. So in general, the equilibrium is defined in thermodynamics at least in three different ways. One is the thermal equilibrium. That means when you have the systems having similar temperatures. Okay, that is, let's say, phase 1 is at T1 and phase 2 as T1, T2. When these two temperatures of these two phases are equal, we will have a thermal equilibrium. Similarly, if pressures are equal, we will have mechanical equilibrium. And if we have chemical potentials equal on both the sides, then we will have chemical equilibrium. Okay? And together we can call it as a phase equilibrium. Okay? So typically we will be interested in the chemical potential, and further these all these three quantities, chemical potential, temperature, and mechanical equilibrium, that is pressure, is involved in a more general quantity, which is Gibbs free energy. Okay, so G basically depends on all these three, mu as well as P1 and P and T. Okay, and what we want is just like when equilibrium, thermal equilibrium is for T1 equal to T2, mechanical equilibrium is for P1 equal to P2, the pressures are equal, and chemical equilibrium is for when the chemical potentials are equal. Similarly, the thermodynamic potentials values, that is the Gibbs free energies values during the phase transition, will be equal. Okay, so for phase 1 and phase 2. So this is how now your the phase diagram will look like if we talk everything in terms of the Gibbs free energy. So we have this first region where the solid phase of the matter exists, and then we have a liquid region, and then this is the gaseous region. So we are naming this as phase 1, phase 2, and phase 3. So there will be boundary between phase 1 and phase 2. That is the point actually, or that is the curve along which across which you can have phase transition. So along this curve, at any point, at all the points, we can have phase transition. That means at all the pressures and temperatures along this curve, we can have phase transition. So, and apart from the pressures and temperatures, we will also have the Gibbs free energy of phase 1 equal to Gibbs free energy of the phase 2. So that is what this line represents, or this equation of this line represents, or this curve represents. Similarly, we can have phase equilibrium between liquid and gas, that is phase 2 and phase 3, when we will have G2 equal to G3. And same way, we can have equilibrium between phase 1 and phase 3 when G1 is equal to G3. And all these three curves will might intersect depending on the system, and that there you will have a triple point. Okay, that means basically at this point G1 is equal to G2 is equal to G3. Okay, so all three phases coexist at this point. That's what we mean by triple point. Okay, so let's just do some mathematical arrangements. So let's define a quantity which is the difference of this G1 and G2. That means, let's say we are somewhere off from this curve, then we are here, then there will be some difference between G1 and G2. G1 stands for the phase, the Gibbs energy of phase 1, and G2 for Gibbs energy of the phase 2. So that if they are not in equilibrium, if these two phases are not in equilibrium, then you will have G1 minus G2 equal to not 0. So let's say that quantity, the difference between these Gibbs free energies, is defined as some small g, okay, which is of course will be function of these pressures and temperatures. So now this quantity is of our interest. We have to make this equal to 0 so that these two phases are in equilibrium. Okay, so we will use this quantity, and let's say, in the search of uh, phase transition or phase equilibrium, sorry, uh, we change this pressure and then also temperature by some small amount, like G with pressure P plus dP now and T plus dt. So if this is a smoothly varying function, we can express this in terms of Taylor series. Okay, so we know that Taylor series will have G of Pt and then first order derivative, partial derivatives of this small g with respect to pressure and temperature, and then there will be second order derivatives as well and higher order derivatives as well. Okay, so let's uh, go ahead. So, or let me just quickly introduce that whenever there is discontinuity in this first order derivatives of the Gibbs free energy, ultimately these are the derivatives of the Gibbs free energy, because G is equal to G1 and G1 minus G2. So if you substitute here, it will become double G1 by double P minus double G2 by double P. So they are ultimately the Gibbs free energies partial derivatives with respect to pressure and temperature. So if these first order derivatives become discontinuous, then this is the transition which accompanies this or which exhibits these discontinuities are first order transitions, okay? First order phase transitions. And if they are these first order derivatives are continuous, then there will be discontinuity in the second order derivatives, and that those kind of transitions are called second order phase transitions. Okay. So we'll look at first order phase transitions in this class. Next class we will talk about the second order phase transitions. So in first order phase transitions, we will have when there is a phase transition, this difference between G1 and G2 will be equal to 0. That means this quantity G small g will be equal to 0. And if we solve this equation, we will get we'll solve this equation for this pressure and temperature, then we will get this curve which we discussed last slide. Okay, that phase diagram, we will get that curve. So if you are at triple point, then of course G1 will be equal to G2 and G2 is also equal to G3. So that is your triple point condition for triple point. And these are the quantities which will vary discontinuously. So before that, I would like to come back to this. So at this point, that is your triple point, G1 is equal to G2 equal to G3. Right. Now let's look at these curves. So these curves are basically like Gibbs free energy changing when you changing with temperature, specific volume V changing with temperatures, entropy changing with temperatures, and the heat capacity changing with temperature. And this line, dotted line, represents a temperature at which the phase transition happens. So you'll see that G is more or less continuous function, whereas specific volume and the entropy are a discontinuous function. Remember, entropy is also related with the temperature, sorry, with the internal energy, and therefore you can think of internal energy being discontinuous here. The heat capacity, we will discuss this. So what we are saying is the Gibbs free energy varies continuously. However, there is a small change in at the transition temperature. What changes is basically the slope of the curve. So at T0, the slope of the Gibbs free energy as a function of temperature changes. So if we have T less than T0, that is this region, okay, T less than T0, T0 is this temperature, transition temperature. Then double G1 by double T, that is this slope of this curve, is greater than this curve. It's negative slope, therefore it is this slope is more than this slope. Okay, so let's just continue this, and I need that figure, particular figure, so I will just go to that figure. So now we are going to find out next values of pressure and temperatures at which the small g becomes 0. Small g means the difference between the Gibbs free energies between between phase 1 and phase 2, or it can be phase 2 and phase 3 or phase 1 and phase 3. So we have to find out at what value of pressure and temperature we will have G1 equal to G2, that is G small g equal to 0. So what we can do is again express this in terms of Taylor series. So This is your Taylor series. We are restricting here only till first order derivative because this is first order phase transition. So we will have first order derivatives discontinuous. So therefore, second order derivatives cannot be defined, or we don't have to consider them right now. So So look at this equation now. So we want this quantity to be 0, okay? And we already have this quantity equal to 0. Okay, if you are having phase equilibrium if you are along this curve at any pressure and temperature along this curve, you will have small g equal to 0. And now we want to find out. Let's say I change the t by dt and p by dp. Then and still we want to have phase equilibrium, so that is this point p plus dp and t plus dt, so that is 0, and it was already 0 at p and t. So we got that this first order derivatives, partial derivatives with respect to temperature and pressure, that addition summation will be equal to 0. And let's now define the quantities, or you can get that from your definition of Gibbs free energy, which is H minus Ts, where H is H is U minus U plus PV. Okay. So from that you can, if you differentiate the G with respect to pressure, you will get the specific volume, partial derivative, therefore only specific volume. And then if we differentiate this, that G is equal to H minus Ts, or U plus PV minus Ts. So there again, if you differentiate with respect to T, you will only get S with minus sign. All right. So that equation we can make we can rearrange and substitute in here. So remember, this is the derivative of capital G, that is Gibbs free energy, and this is the derivative of small g. So small g is g1 minus g2, so therefore this will be v2 minus v1, and this will be s2 minus s1. So if we substitute that here, this gives us this s2 minus s1 times dt and v2 minus v1 times dp, and that is equal to 0 with minus sign. So therefore these two quantities are equal. So we can write dp by dt equal to s2 minus s1, or v2 upon v2 minus v1 equal to delta s upon delta v. That is change in entropy with respect upon change in volume specific. So this dp by dt is nothing but a slope of these curves, this phase equilibrium curves. So the slope of the curves basically depend on how the entropy changes and how the volume changes. Okay, depending on that, the slope will be positive or negative, that we can determine. So another thing we can introduce here is the latent heat, concept of latent heat. So when we have G equal to G2, and let's say we are maintaining that at the same pressure and temperature, we're not changing it. So what will happen? So basically, if we take G is your again H minus Ts. So G1 will be equal to H1 minus T times S2 minus S1, because temperature is constant. Similarly, G2 will be equal to H2 minus T times S2. So if we just substitute that and make them equal, we will get this H2 minus H1 equal to T times S2 minus S1. And this difference of enthalpies between phase 1 and phase 2 is called as your latent heat. So now we are going to use this expression in this equation of dP by dt and substitute it for L. Okay, so this equation traditionally is known as Clausius-Clapeyron equation. Okay, and there we are now going to substitute that in terms of L instead of delta S. The reason we are doing this, because it is very difficult to measure the change in entropy. Instead, it is very easy to find out the difference between the enthalpies of phase 1 and phase 2. Therefore, the latent heat is easy to determine instead of the change in entropy. Therefore, we are writing everything in terms of latent heat. So dP by dt is now equal to L by T V2 minus V1. So this is like L by T times delta V, change in volume. So this is the relation again in terms of latent heat, the Clausius-Clapeyron equation in terms of latent heat. So this equation basically explains a lot of things for us. So for example, we again have this curve, phase diagram curve. in terms of G1 and G2 phase equilibrium curves. So we already have seen that G is a continuous function, right? It does not change. It does not change discontinuously. But the first order derivatives of the G, the Gibbs energies, they change discontinuously. And first order derivatives are nothing but volume and entropy that we have seen. The heat capacity. This is something which I wanted to discuss before. So let's just go back to that. Yes, here. So you'll see that heat capacity is slightly increasing with temperature and then suddenly goes to very high value, and then again for phase 2 it again starts increasing very slowly. Otherwise normally it is constant for constant, more or less constant, but at phase transition it just suddenly jumps and comes down. So what happens basically is during the phase transition the heat is basically used for transforming the phase of material from, let's say, solid to liquid. Now the heat capacity we define as the amount of heat required to raise the temperature by unit, uh, raise the unit temperature. Okay, you can say 1 degree Celsius and 1 degree Kelvin. So now that is not happening because the heat is used to make the transition, not to raise the temperature. So the temperature is constant during the phase transition. We know that, right? So if the temperature is constant, there is no change in temperature, but we are keep on supplying heat. So that means that the heat capacity is very large at that temperature. Okay. So therefore, the heat capacity shows very large value during the transition, and then again it behaves normally for after the phase transition has happened. Okay, so that is what we are talking about, the heat capacity. Typically, we will have entropy of phase 2 higher than phase 1. So therefore, the latent heat is always going to be positive. For example, like solid to liquid transition and liquid to vapor transition, we will have higher entropy after melting or vaporization. So let's just try to understand this liquid vapor transition and solid liquid transition. So we understand that latent heat is always going to be a positive quantity, which is T times S2 minus S1, and S2 is always going to be higher because the entropy never, for an isolated system at least, the second law tells us that entropy will never decrease. So therefore S2 is always going to be large. So let's look at the liquid vapor transition. So liquid vapor basically, we can see that the volume change is always positive for liquid vapor transition. So like water becoming vapor, so volume will always be higher for vapor. So that means from classical vapor equation, that dp by dt, that is the slope of this curves, is always going to be positive. That also means that if you increase the pressure, temperature is going to be increased. So if you increase the pressure, the melting point or boiling point, in this particular case boiling point will be increased. So that explains our experimental finding that boiling point increases with pressure. If the vapor pressure is low, now the vapor pressure is something which is, there will be, if you have liquid state, liquid phase, there will be some molecules of, let's say, water, uh, will be surrounding at the boundary of water. Okay, there will be some molecules in the gaseous state. So that is the amount of that, or the pressure exerted by those water molecules is called as vapor pressure. And if that is very low, that means if liquid, it does not like to leave the liquid state easily. For example, for alcohols, it is less. Alcohols, the tendency is less. That means vapor pressure is large, so you can have more vapors in the atmosphere surrounding the liquid phase of that same material. Whereas water, it is relatively low. So if you have very small vapor pressure, that means the volume in gas state is very large than as compared with liquid state, and that is typically true for practical purposes. So in that case, you can neglect this VL, and therefore dp by dt simply becomes LV upon T Vg. It was delta V. Instead that, if we neglect VL, you will simply have Vg. And now we are specifically talking about vaporization. Therefore, this L is called as latent heat of vaporization. And if we use the ideal gas equation for these gases, so we will get Vg equal to RT upon P from that is PV is equal to RT. So this ideal gas equation. If we substitute that here for Vg, then we will get, and just slightly rearrange this pressure coming here, that we bring it here, so we will get dP by P and Lv by R times dt by T square. Okay, here we already have T and this T will come, so it will become T square. And if we integrate it and then take out the logarithm, then we will get, if we integrate it, we will get ln of P. Okay, and then here it will be 1 upon T after integration. And then if we apply the limits from uh, t to tc, we will get this p of t equal to pc of tc exponential, and then lv by r as it is, but 1 by tc minus 1 by t. And if we again, if we might have a relation, typically the latent heat depends on temperature, and if we use simply linear relationship for that, then we will get this equation. If we substitute LV equal to this linear relation in terms of A and B are constants, so we'll get this relation. So these are customized forms of Clausius-Clipperton equations in terms of like liquid-liquid transition. And similarly, we can have for solid-liquid transition. Okay, here instead of LV, we will have LM, that is the latent heat of melting. And here there are two possibilities. Solid liquid transitions can have two possibilities. That liquid phase volume is larger than solid phase volume, that is normal case. So you will have this dt by dp, or you can say the inverse of the slope is greater than 0 is positive. So with melting point, that is the temperature at which you will have melting, increases with increasing pressure. Similarly, uh, if you have another case where the liquid volume is smaller than solid volume, that is like an ice case. Okay. So here dt by dp will be negative, and the melting point in this case will decrease with increasing pressure. Right. So we have, these are the experimental findings basically, and we could explain those by using our Clausius-Clipperton equation. Alright, so we will stop it here at this point. Next lecture we will look at the second order phase transition.